this module, you will learn about the ionization of acids and bases. Of the two beakers, A and B, one contains hydrochloric acid and the other contains acetic acid. Identify which one contains hydrochloric acid. Beaker A, doesn't it? How do you explain that? Its brightly glowing bulb indicates the ability of the solution to conduct electricity, which, in turn, indicates the presence of a large number of current-carrying particles in the solution. HCl, being a strong electrolyte, undergoes almost 100% dissociation in water. As a result, the solution contains a large number of ions that help conduct electricity to a greater extent. Acetic acid, on the other hand, is a weak electrolyte and undergoes very little ionization. Thus, the solution contains mostly unionized acetic acid molecules. Therefore, very few ions are available to conduct electricity, and so the flow of electric current is weak. Hence, the bulb glows very faintly. According to the Arrhenius theory, the strength of an acid and a base is related to the ease with which they function as a source of H+ ions and OH- ions in an aqueous medium. As hydrochloric acid, sulfuric acid, nitric acid and perchloric acid undergo almost 100% dissociation, they are said to be strong acids. These acids act as proton donors. Similarly, bases such as sodium hydroxide, potassium hydroxide and cesium hydroxide are also called strong bases as they undergo complete dissociation in an aqueous medium, furnishing OH- ions. In terms of the Bronsted-Lowry theory, a strong acid is one that readily donates the proton, while a strong base is one that readily accepts a proton. The greater the tendency of an acid to donate protons, the stronger it is. Similarly, the higher the tendency of a base to accept protons, the stronger it is. To understand the statement better, consider the ionization of HCl in water. You can see from the equation that Cl- is the conjugate base of HCl and H3O+ is the conjugate acid of the base H2O. Now, as you can see, there are two acids, HCl and H3O+ in the reaction. Now, which one is stronger? Obviously, HCl. This is because HCl shows a greater tendency to lose protons than the H3O+ ion, and hence, the solution primarily contains Cl- and H3O+ ions. Generally, the equilibrium will shift in the direction of weaker acid, and the resultant solution mainly contains Cl- and H3O+ ions. As HCl is a strong acid, it readily loses the proton. Does this tell you anything about the chloride ion as a base? Yes, it does. HCl is a strong acid, which means that every HCl molecule produces H+ and Cl- ions. This further means that the forward reaction predominates in this reaction. In an aqueous solution, there are virtually no HCl molecules, but only H plus and Cl minus ions. This shows that the Cl minus ion has very little ability to attract the H plus ions in the water, and thus is a very poor base compared to the water molecule. Hence, it follows that a strong acid has a weak conjugate base. Strong acids like hydrochloric acid HCl, sulfuric acid H2SO4, nitric acid HNO3 and perchloric acid HClO4 have a very weak conjugate base like chloride ion Cl- ion, bisulfate ion HSO4- ion, nitrate ion NO3- ion and perchlorate ion ClO4- ion. Now, let's consider the dissociation of acetic acid in water. It is a weak acid. The term weak acid means that it undergoes dissociation to a less extent, and thus, very few ions are present in the solution. This means that the backward reaction predominates in its aqueous solution, and acetic acid remains largely in the undissociated form. This clearly indicates that the acetate ion strongly attracts the protons in the water, and thus it is a strong base compared to the water molecule. Hence, you can infer that a weak acid has a strong conjugate base. Weak acids like acetic acid CH3COOH and hydrofluoric acid HF have very strong conjugate bases like acetate ion CH3COO- ion, fluoride ion F- ion respectively. You might have observed that during acid-base titration reactions, indicators like phenolphthalein and bromothymol blue are used. Generally, indicators are weak organic compounds that exhibit different colors in acidic and basic media. For example, phenolphthalein is colorless in an acidic medium and pink in a basic medium. This change in color helps us in identifying the end product of an acid-base reaction. Observe the two reactions of the dissolution of ammonia in water and the ionization of HCl in water. What do you infer? You can see that water is capable of acting both as an acid as well as a base. Pure water is a poor conductor of electricity. Conductivity measurements show that water ionizes to a very limited extent. This equilibrium constant Kc for this equilibrium can be written as Kc is equal to the product of concentration of H plus ions and concentration of OH minus ions divided by concentration of H2O. Since the ionization of water is negligible, the concentration of water can be taken as constant. Thus, the concentration of H2O can be incorporated in the value of Kc to give a new constant, Kw, called the ionic product of water. The ionic product of water, Kw, at a given temperature, is defined as the product of the concentrations of the H plus and OH minus ions in water or in aqueous solutions. Experimentally, the concentration of H plus ions at a temperature of 298 Kelvin was found to be 1.0 multiplied by 10 to the power of -7 moles per liter. The dissociation of water produces equal number of H plus and OH minus ions, and hence the concentration of OH minus would also be equal to 1.0 multiplied by 10 to the power of minus 7 moles per liter. Thus, at 298 Kelvin, the ionic product of water, which is equal to the product of the concentrations of H plus and OH minus ions, is equal to 1 multiplied by 10 to the power of minus 7 raised to the power of 2 moles per liter. This is equal to 1 multiplied by 10 to the power of minus 14. Hence, the value of the ionic product of water at 298 Kelvin is equal to 1 multiplied by 10 to the power of minus 14 moles square per liter square. It must be remembered that Kw, being the equilibrium constant, depends on temperature. The aqueous solutions of various substances can be divided into neutral, acidic or basic, depending upon the relative amount of H plus and OH minus ions. In neutral solutions, the concentration of H plus ions is equal to the concentration of OH minus ions. In acidic solutions, the concentration of H plus ions is greater than the concentration of OH minus ions. While in basic solutions, the concentration of H plus ions is less than OH minus ions. The concentration of hydrogen ions is commonly expressed in terms of the pH scale, which was introduced by S.P.L. Sorensen. The P in pH comes from the German word Potenz, meaning power, and the H from the concentration of H plus ions. The pH of a solution is defined as negative logarithm to the base 10 of the molar hydrogen ion concentration in a solution. Thus, the pH of a solution containing hydrogen ion concentration of 10 to the power of minus 4 molar will be equal to 4. You have seen that at 298 Kelvin, the concentration of hydrogen ions in pure water is equal to 10 to the power of minus 7 moles per liter. Thus, the pH of pure water is 7. Thus, for neutral solutions, the H plus ion concentration is equal to the OH minus ion concentration, and the pH is equal to 7. For acidic solutions, the H plus ion concentration is greater than the OH minus ion concentration, and the pH is less than 7. For basic solutions, the H plus ion concentration is less than the OH minus ion concentration, and the pH is greater than 7. The pH of some common substances is shown here. The pH of a solution can be roughly estimated using a pH paper that gives different colors in solutions of different pH values. For accurate measurement, pH meters are used instead of pH papers. A pH meter is an electronic instrument that measures the pH-dependent electrical potential of the test solution. As we saw earlier, the ionic product of water at 298 Kelvin is equal to the product of the concentration of H plus and OH minus ions, which is equal to 1 multiplied by 10 to the power of minus 14. On taking negative logarithm on both the sides of the equation, we get negative log of Kw is equal to negative log of H plus and OH minus ion concentrations, which is equal to negative log of 1 multiplied by 10 to the power of minus 14. Negative log of H plus and OH minus ion concentrations can further be written as negative log H plus ion concentration and negative log of OH minus ion concentration. This is equal to negative log of 10 to the power of minus 14. As negative log of Kw is equal to pKw, negative log of H plus ion is equal to pH, and negative log of OH minus ion concentration is equal to pOH. Thus, the ionic product of water at 298 Kelvin, pKw, is equal to pH plus pOH, which is equal to 14. Based on the pKw value, the pH scale has markings from 1 to 14, and the nature of a solution as neutral, basic or acidic is determined depending on its value on this scale. This brings you to the end of this module. In this module, you learned that according to the Arrhenius theory, the strength of an acid and a base is related to the ease with which they function as a source of H plus ions and OH minus ions in an aqueous medium. In terms of the Bronsted-Lowry theory, a strong acid readily donates the proton and a strong base readily accepts a proton. Strong acids have weak conjugate bases, and weak acids have strong conjugate bases. The ionic product of water, Kw, at a given temperature is defined as the product of the concentrations of H plus and OH minus ions in water or in aqueous solutions. Aqueous solutions can be categorized as neutral solutions, acidic solutions, and basic solutions, depending upon the relative number of H plus and OH minus ions. The pH of a solution is defined as negative logarithm to the base 10 of the molar hydrogen concentration in it. Based on the value of the ionic product of water, the pH scale has values from 1 to 14. A solution with pH value 7 is neutral. Less than 7 is acidic, and more than 7 is basic.